I was going to say this is going to be the best class ever, but David changed my mind. No, I'm just kidding. Okay.
That's recorded.
All right. Okay. Everybody has their notes packet out. We're starting chapter 5. Okay, so in chapter 5, we are now going to start working backwards. So up until this point, we've been doing derivatives, which kind of go forward. Like if you start with position, then you take the derivative, you get velocity. Take the velocity's derivative, you get acceleration. Okay, so now we're going to work backwards. We're not going to get to that point just yet. We're going to look at some really basic examples. The first one being distance traveled. Okay, so consider the following problem. A train moves along a track at a steady rate of 75 miles per hour. Okay, and again, it's steady, so that means it's a constant rate. And it's going to be traveling from 7 a.m. to 9 a.m. So what is the total distance traveled by the train? Okay, so this is really pre-algebra, Algebra 1 concept, but we're going to look at it, a variation of it in calculus. So we're going to use D equals R times T. What's D equal? What's D is distance, R is rate, T is time. So D equals the rate. Okay, so the rate was steady. It was 75 times T. So if it goes from 7 a.m. to 9 a.m., that's 2 hours. Right, so we get 150 miles. Yeah, if the rate is in miles per hour and this is hour, think about it. If I have miles per hour and I multiply by 2 hours, think of this as, when you cancel units and so on, right? The hours would cancel and we end up with just miles. That's how we know units. Okay, so let's make a connection with this formula and the graph of the velocity. So one of the things that we said was that the rate was constant. It said a steady rate of 75 miles per hour. So that means my velocity, right, here's velocity. So basically, it stays constant at 75.
Is it time? The velocity?
Yeah, this is velocity. This is v of t. So we're just saying v of t is equal to 75. It's not changing. It's just a constant rate. Think y. So when we graph a constant function, that's a y equals. It's a horizontal line. And what we want to do is we're looking at, okay, so let's say this is at 7 a.m. We don't know if it started earlier. We just want to focus from 7 to 9 a.m. So what we're really looking at is this rectangular area. So we can think about this. So the area under the line from 7 to 9. Well, that's just base times height. You see that? It's just a rectangle, though. So the area, the base is 2. The height is 75. So we get 150.
Okay.
So what I'm trying to make the connection between distance equals rate times time, and another representation is this area under the line makes a rectangular region. So it's like the distance equals rate times time. So here's your rate, your time goes across. So think of the rate as like the height of the triangle. The time is the base of, or did I say triangle? Rectangle. Rectangle. Okay. No? Yes? So if it's a constant rate, I will tell you, anytime you have a constant velocity, it will always be a rectangular region. Okay, if you have a constant velocity, the area under the curve, we say curve could be a line or something like a y squared or x squared or something, but specifically I'm looking at a constant rate. The line's going to stay straight, so we will always have this rectangular region.
I didn't get one.
Well, okay,
What's the next one?
that's the next one. So we just kind of talked about that. So let's turn to the next page. So of course that's the basic one, and obviously we didn't need any calculus for that, which means we're going to consider what if the velocity does change. So what if the velocity, I don't know, it might go from here and then here. So what if this is my velocity function now? All right.
Uh-oh.
Okay, so I can still look at from 7 to 9 in the morning, but it's no longer a rectangle. So we want to look at, is there a way to figure out this area? Because if we can figure out this area, we will have the total distance traveled.
Well, if we figure out like the minimum, the local minimum, right there, can't we figure out the height?
Okay, so we're looking for the total area under the curve. If we can find that shaded region, then we have our total distance traveled. Okay, so we're going to do this not with a big rectangle, but with smaller rectangles. Okay, so I just had some questions here. Would the area of this irregular region still give the total distance? We kind of answered that already. Yes. Okay, so Newton and Leibniz. Okay. Also agreed that the area under the curve will represent the total distance traveled. So what we're going to do is take that region.
Is Newton really good at calculus?
No. He just came up with, you know.
Newton's so
Most
good
of
at
it.
physics.
All right, I don't remember what my curve looked like above. Hold on. It kind of went up and then down. I'm just recreating it. Did it like go like
Yeah.
this?
Yeah.
Was it something like that? Okay, just pretend it was approximately the same curve. So what we're going to do is we're going to take this region and we are going to partition into many tiny subintervals. Okay, so imagine that you're getting really small.
I'm
And
sure this is the best way to do it.
yeah, well, I'm getting to that point. So you can make these rectangles in a number of different ways, which we're going to look at next.
What is this?
And the smaller the intervals become, right, the more accurate you're going to get more rectangles, but you're going to get more accuracy. Okay.
But we didn't
No, you don't need to worry about drawing this part. Just draw some rectangles, okay? So just looking at this, know that if I can figure out, because we know how to find the area of a rectangle, right? So if I can figure out the area of this rectangle, this one, this one, this one, this one, add them all together, I'll get a good estimate for the area under the curve, which will tell me how far the train or whatever it might be has traveled.
Roughly.
So what we're going to look at in this first section are estimates.
That's easy.
Then we'll find out later how to find exact.
So do you actually count how many times it's split up?
Well, so we're going to be adding these areas. We'll look at that the next page. What's that?
There's a highlighter.
Oh, I have a highlighter sitting here. All right, guys. So our rectangular approximation method, there are 3 different ones that we're going to use. There's one, and I'll tell you right here. So each rectangle, think of a rectangle, has width and it has height or base and height, however you want to think of it. So the width of each rectangle is determined by the length of each subinterval. So imagine like this example that I had here. Each of these subintervals, right, that's going to be the width, and then the length will be the height of each rectangle. So that's where, wherever the function, whatever the function's value will be, that will determine the height. Okay, so we have left-hand endpoint, we have right-hand endpoint, and then we have midpoint approximation. So we have 3 different approximations that we could use. You need to know how to do all 3 of them. Okay, and it's easier to see on the pictures to understand each one. So let's just go down. Okay, so in example 1, you'll see that I drew, there are 3, well I didn't draw, but I copied in here. I have the curve f of x equals x squared from 0 to 3, drawn 3 times. One I'm going to do left-hand approximation, one I'm going to do right-hand approximation, and one I'm going to do midpoint. So if you look closely at the rectangles, you'll notice that each one, the rectangles are drawn at a different location, if you will. You see how like this one here,
Like their lengths vary depending on how.
right? So the bases are all the same. Right? The bases are all the same, but the heights are going to be determined by where the endpoint is going to hit. So let me, let's look at left-hand approximation first.
What is range?
Rectangular approximation method, right at the top.
LAM.
So L round, left-hand endpoint rectangular approximation method, which I will just call L round. All right, so now there's some important information in the directions here. One of them, so first of all, we had, it goes from 0 to 3 with 6 subintervals. One thing I forgot to put in there, we're going to use 6 subintervals of equal length. So if you look at here, well, if this is 3, right, this would be 1, this would be 2, this would be a half here. You agree with that?
Why?
Why wouldn't
I'm just labeling the
Oh, how you
the subintervals. What's right in between 1 and 2? 1.5 or 3 halves, I'll just put in.
Write it in.
You don't need to, but I'm just showing you that this will be 5 halves.
I know. This is super Jewish.
Just try to work it out.
Oh, it's from downstairs.
Is the thing
It's
with
the
Yiddish concert?
It's in Mr. Stein's music
Yeah,
room, which is right under the ESP. Sorry, we're being a little bit of detectives.
All right, are we okay so far? Now, what is the length of each subinterval here? What's the length of each sub? Half. Okay, so each subinterval has, how can I write that? So each subinterval has a length of 1/2, which means kind of the base of each rectangle is 1/2. How would we figure out the height?
Based on the
Okay, so here's what we're going to do. For the left-hand approximation, so imagine here, the first interval goes from 0 to 1/2. So think about the left-hand endpoint would be f of 0, which would be 0 squared.
Oh, hey.
So my first rectangle isn't really even a rectangle. There's no dimension to this first rectangle I have here. The next one, okay, so the base for the next one also has a base of 1/2. But if you see it, it's really small. What's the height of that rectangle? So we use the left endpoint, which is 1/2, and we square it. Actually, I should have put the square on the outside.
So we just keep
on using whatever the next base is squared. So the next one's going to be 1 squared, and then the one after that 1/2 squared,
Oh,
and then
Right.
2 squared.
These are gonna be tedious.
They are. So I'm going to show you on your calculator a way that you can verify your answers. I usually, on a quiz or a test, I would usually only have, this has 6 sub-intervals. Most of the time I'll ask for mostly just 4. So the next one, this is my next rectangle. So you have, it goes from 1/2 to 3/2. So my left-hand endpoint is at 1. So it's going to be 1 squared. That's the height. Okay. My next rectangle goes from 3/2
Three
to
on
2.
the line.
So it's going to be 3/2 squared. That's going to be the height where it hits on that graph. Next one is going to go from 2 to 5/2. So again, the base, notice the base is always going to be 1/2, and I'll show you, you could have just put the 1/2 all the way out in front. This is going to be 2 squared. Well, we're doing the first one. I'm just trying to show you it's base times height plus base times height plus base. You're adding. Now, at the end, you should have 6 added together because it was 6 sub-intervals, so you should have 6 rectangles. I have 1, 2, 3, 4, 5. I need one more. The last one, yeah, but the last one goes from 5/2 to 3. 3 is a right-hand endpoint. Remember, this one was just using the left-hand endpoints. So it's going to be 1/2, oops, and then 5/2 squared. So with left-hand approximation method, with the left hand, we never use the last one. We use the first one, which is 0. And then we use 1/2, 1, 3/2, 2, 5/2. We don't use the last one. Look at this last one here. Does that hit the curve? No. So it's not the height of the rectangle that we want to use. So we don't use the 3.
How do you know that 5/2 is the height though?
Because if you, it's 5/2 squared. So wherever this hits right here, that's going to determine the
That's
height
what
of
y
that
is.
rectangle.
Oh, okay. Okay.
So
I got
plug this all
6.875.
You get,
Yes,
yeah, just to save some time.
Okay.
I got 6.5.
But technically, you could just put a half on the outside.
Okay.
Multiply all those.
You guys are, oh, I didn't square.
So if you don't want to have to put that 1/2, and that's what we'll do for the next one. Notice the base is always going to be 1/2, so you could have factored out the 1/2 at the beginning and just done the height squared, you know, or that, you understand, not the height squared, but the value squared plus the value squared plus the value squared, so on. Are we okay with that?
There aren't any units.
Put any like units?
There's no units, so the approximate area under the curve using these left-hand endpoints is 6.875. Now, just looking at our rectangles, do you think this is an under approximation or an
Yes.
over approximation?
Approximation.
Under, because you can see that there's all these gaps here. So when we look at the next example, which is right-hand approximation, it's going to be an over approximation.
Oh, then
Now,
find the mean of all 3.
okay, so for the next one, for our RAM, if it makes it, I think it makes it a little easier. Are you okay if I just take out the 1/2?
Yeah.
Okay, now, here's where I want to be really clear. Notice this time we're not going to use, remember how we started at 0 because that was a left-hand endpoint. Now we're starting at 1/2. So it's going to be 1/2 squared. Okay, and then the next right-hand endpoint goes here, right? That's going to be 1 squared. The next right-hand endpoint is 3/2 right here. So it's going to be 3/2 squared. The next right-hand endpoint is going to be 2 because it hits here. So 2 squared. The next right-hand endpoint is 5/2 because that hits up there. And this time we do use the 3 because look where 3 hits right there. That's the height of my last rectangle. 3 squared is the height. So this is really not much different than the previous one. It's just that we didn't count the first one, but we counted the last one.
Well, how do you write your answer? Just
Oh,
R
wait,
RAM equals 11
Yeah.
points.
Sorry,
so-
Chase.
Oops, whoops. What do you guys get for this?
I got 11.37.
That's right.
Same.
Okay, yeah, there we go.
That should be what you get.
That's what I originally got for the first one because I thought you had that. There we go.
So left and right hand endpoints are the easiest one. The midpoint, I know, the midpoint is a little, it's a little trickier
More
because,
Necessary.
One word.
maybe?
so in terms of the midpoint, we still have all of our subintervals are 1/2 in length. However, we're using the midpoint of each subinterval. Okay, so for example, the first subinterval goes from 1 to 1/2. So the midpoint would be 1/4.
What is the really bad with fractions?
So there's gonna be. So we don't do we do the midpoint of the midpoint as opposed to midpoint.
The midpoint of the mid. Well, so for example, our next subinterval goes from 1/2 to 1. What would be the midpoint of 1/2 and 1?
So
3/4.
So we do the midpoint of the midpoints as opposed to the real midpoints.
1/4.
The midpoint of the mid. It's just the midpoint of each
No,
subinterval.
that's what I'm saying. Like, because 1/2 and 1, those are like the midpoint.
Oh,
So I like.
I see what you're saying. You're saying the midpoint of like 1, 2.
Yeah.
Got it. That's fine. If whatever
It was
helps you to
midpointception.
And then you guys will see the pattern now. What's the midpoint of 1 and 3/2? Come on, you can do it.
5/4.
5/4.
Yay!
Okay, look at the pattern.
How do you
Oh, it's all odd.
Oh goodness, what's the next one?
7.
When should we stop? How many should we have?
6.
It would most likely be easier to put in the calculator decimals, right?
Okay, use decimals, that's fine.
Fine.
If you prefer decimals, decimal 0.25, 0.75.
How do you find this?
11.
Do you do half minus half, 1 minus half?
So how do we find the midpoint of something? This goes back to like geometry for or actually not always.
Y2
It's-
minus Y1.
No, that's slow.
Just do a half
It's-
Okay, or you could do that, but do 0 plus 1/2 on your calculator and divide by 2.
Wow!
Do 1/2 plus 1 and divide by 2. Do 1 plus 3/2 and divide by 2.
No, I like
Okay, so when we get this, we get about 8.9375.
Hey, can you just, I just,
Yeah, I know the same thing.
my calculator is yogurt stock, so.
Why did we go from 5/1 to 5/5?
8.9375.
That's how to take out your calculator.
Okay, now we're going to verify this on our calculators with the programs that I just put on. Well, just one program in particular. We're not going to use the other two
How do you get
later.
that?
Okay, so press.
Program. It's
Not
a
like that.
button called program.
Ah.
It's like in the middle of the top.
Okay, so if you're on your home screen, when I say home screen, just this blank. So we're going to press program. We want to use the Riemann. So if you have like formula programs that you have it in there, whatever, it's fine. But just, we're not going to edit, we're just going to execute. So we're going to press, you could either type number 1 or just press enter if that's the one
I
that
don't
is.
have.
I did program Riemann.
Wait,
Okay.
is it Riemann?
It's
Yeah.
Riemann.
But it's for 2 on that.
Yeah.
Yeah,
same.
it's fine.
Okay, because you had a program than it was previously. It doesn't matter where it was. So next thing we're going to do, just press enter.
Whoa.
Okay, so it's going to ask you to type in f of x. So what function were we using this whole time?
X squared.
Press enter again.
Press enter.
Oh my god, thank
Okay,
you.
so what function were we using this whole last example? X squared. X squared.
Enter.
Hold on, I want to make sure we're all on the same page. Everybody there?
This calculator is like a machine. It does my work for me.
We're good? Olivia? Alexis,
That's actually
Maytel?
exactly
Brett?
what it is.
You good?
No, it's
Okay, I want us all to be on the same page because this is how you're going to check your answers on a quiz or a test. I'll want to see the setup, but you can always check your
Is
answers.
it okay that my thing has X, a little arrow, and then 2?
Yeah,
Same thing.
yeah.
Yes.
As long as it's the same.
Okay, press enter. Now it's going to ask you for a lower bound. So remember, we were only looking at the graph from 0 to 3. So we're going to type in 0. And of course, I have my calculator too low. There we
Wait,
go.
why did you take 0? Oh, because that's
So I want
lowest.
0.
So 3.
Press enter.
3.
Next it's going to prompt you for the upper bound. So we're going to type in 3. Right? It was from 0 to 3.
What's a partition?
Okay, next question, partition. So we broke this up, it says into 6 subintervals. So subintervals and partitions are the same thing.
So do we write all of them or just how
Just
they're
write
all
6. Type in 6.
Beyonce is in our calculator.
6 because there's 6.
There are
trees.
6
It
subintervals.
tells me to press enter.
That is correct.
Why do you need trees?
Okay. So what's nice is that your calculator will graph the function for you in the window that fits the graph, the part that you want, which is really nice. So it's going to shade in this region. So remember, what were we looking for?
That area.
We want the area under that curve. So it will even prompt you. It says right here, press enter. So we're going to press enter. Now, your calculator will have these choices. So we have left sum, right sum, midpoint. We'll learn about trapezoid tomorrow.
This is so cool.
And then the definite integral. So press 2. Now what's nice is it will do the rectangles for you.
Why does it say trapezoid?
It's so cool.
Oh my god, that is so
We're doing left.
And look, here's your answer.
So
6.
that's the one we choose. I'm setting it on right, left, and then midpoint. So you choose.
Okay, now guys, this is important. So 6.875. You can verify each one. So just press enter and it'll take you back to that screen. So then
so nice.
number 3. Here we go. It's going to graph the right-hand endpoint, 11.375. We can confirm that that's what we got.
This is crazy.
Okay, midpoint, number 4. So we'll press 4.
Let's not tell you.
Oh, trapezoid sum is the next
Okay,
one.
there's our result. Now, I'm going to show you one more thing. Press enter. Trapezoid we'll do tomorrow. Right here, it says DEF. That's the definite integral. So what this will do, which we'll learn later on, is it's going to give you the exact area. So it's as if those rectangles got infinitely smaller in some way. You know, understand what I'm saying? Like the partitions, there are infinitely many partitions. So look at the definite integral. We got 9. So when you look at the results, you can determine which one was the closest approximation, the midpoint. It's not always the case, but in this one it was. Now, one more last thing. If you do not quit your program, your calculator is going to stay in like the weird mode. So you need to make sure that you press number 7 each time that you're done with the program. If you don't,
Number 7?
if we're done with that program for right now, so just go ahead and quit.
Now it's normal.
Now it's back to normal. If you forget to quit it, the mode will be in like parametric equations and you don't want it, and so
Will you help me?
I will help you. Let's go to the next.
Wait, something. I just need.
Why do you have to press number 7?
I know, but I like touched something and then I put a plus sign in that and I ran up on that and
I pressed quit and it didn't
Yeah.
quit.
Oh,
These look like little flowers.
Yeah.
And good for you.
It's really good for you. That's why it tastes so bad.
doesn't taste bad.
Oh,
That's what I'm saying. You gotta quit it correctly. Press number
Yeah,
7.
it's different.
I have it
I mean, my mom like
We're literally eating flowers.
oh no.
Wait, we have to quit it?
When you're, I'm just showing you that you have to press number 7 to correctly quit the program. Press enter. Press enter. Number 7 is quit.
Wait, why are you
Mine's
doing
still
that?
not clean.
Ow. What do you mean?
Is the stock yummy?
Yeah, it's like sweet.
What?
As long as we can get through this one. I showed you the calculator program, but I want to show you one more example. Okay, so let's look at a problem where we don't have the functions equation. We just have a table. So the table below shows the velocity. So here's your velocity in inches per second of a model train moving along a track for 10 seconds. So this train does not have a constant velocity. We can see that it increases and then it gets slower. And then over here, it might speed up a little bit and then slow down again. So we're going to estimate the distance traveled by the engine. We're going to use LRAM. and RAM. So for part A, unfortunately, if
We
you
write small.
no, you don't need to. If you don't have the function, you can't use the calculator program. So you can only use them when you know, like, it follows the curve x squared. This is a random function. We don't know what the equation is. We just know the values. Okay, so LRAM says right here, 10 subintervals of length 1. So that means the base of each of our rectangles is 1. So you could put 1 times the height plus 1 times the height, or just remember the whole thing's multiplied by 1. Okay, so you
Yes.
could, if you really want, put a 1 on the outside. Do you really need it? No. But I'll just leave it in there just to show that that's the base. Now, this is really nice. It's actually a lot easier than the last problem because there's no function. We just look at the result. The velocity is going to tell us the height of each rectangle.
Yo, so that's gonna be very specific.
Yes. So we just have to choose the values. Now, since
12
we're
plus
starting, again, think of the first subinterval goes from 0 to 1 second. What would be the left-hand
Zero.
endpoint? 0.
But it's 0.
Plus. I know, I'm just writing it in there so it's not, so you don't forget it. Now, the next one, just gonna erase that for a minute. The next one has an interval from 1 to 2. Okay, so still, that's 1 to 2. What is the left-hand endpoint? 12, because it goes to 12 to 22, but we just want the 12. And then the next one. So what you'll notice here is we're going to end up using all of these numbers, except the
gonna be the
last
same either
one.
way.
You don't want to use that last one. So it's just going to be 0 plus 12 plus 22 plus 10 plus 5 plus 13
No, 0.
plus
Those
11
zero because it's the
plus
number.
6 plus 2 plus 6.
And all RAM is gonna be the same thing because you move the 0 from one side to the other. Yes, this is true.
Wait, why'd you skip that whole?
Okay, raise your hand if you, what's the question? Okay, but this is not a function. The function is represented by the values that we were given in the table. So there's no x squared. Were we given a function of y equals x squared? The only reason we squared, that's why we squared. Right. Somebody go ahead and add that all together for me.
87.
Wait, why did you didn't include the time?
Okay, so that means, hold on, just real fast, guys. For this, it was moving in inches per second. We were given the time intervals were in seconds. So that means I get a result. How far did the model
Inches.
train go?
Square.
87 inches. No, it's just a linear measure. Now, I know we're running out of time here, but for our RAM, I think some of you realize that it's going to be exactly the same thing because instead of crossing out this last one, so with right-hand endpoints, we kind of ignore that first number and we just use the rest of
It just so
them.
happens that they're both 0.
It just so happens they're both 0. It's not always the
One was 2
case.
and that one was 4.
Right, so instead it would be like starting out with 12 and then 22.
Oh, yeah.
And then 5, and then 13, and then, sorry, I'm running 11, 6. It's just like we would add the, oh no,
Oh, no.
you get the idea.
Yeah.
You guys get the idea? It's just, it's like the zeros added at the end of this one instead of the beginning, but it's kind of irrelevant. So we get 87 inches.
Okay, I'm confused. Oh.
The last problem was just practicing on your calculator with the program. That's all.
Are we gonna get homework from with calculators?